Welcome to the technical track of the Data Science Along YouTube channel, your place to acquire skills casually. In this talk, you'll learn from Daryl, Kang, lead data scientist at Forbes, how data science and NLP supports journalists and research process by providing a quick overview of the news landscape at a glance.
Hello everyone. So today we'll be exploring an important concept in NLP, or natural language processing, called text vectorization, or also known as word embeddings. So specifically, we'll be exploring its applications in the space of news media and how we would use that to summarize clusters of related news articles within a greater developing story. So the space of news media is largely driven by the journalistic process, which here can be broadly categorized into three stages, so to speak. So the first of which is the ideation, where that's the phase where we decide on the topic, gather more information, and conduct further research to see certain leads. And then we have the creation phase, where we do the actual writing, the editing process, and finally the distribution phase, where we disseminate our work to various platforms or target audience. So increasingly, AI is playing a bigger role at every stage of the process. So we believe with the right principles, AI works to empower, not to replace the journalists through various data-driven solutions, thus allowing the journalists to focus more on storytelling. But in today's talk, we'll be focusing specifically on the role that AI can play to enrich the task of information gathering and organization within the ideation stage. Perhaps the biggest challenge throughout this process in the information stage is the burden of sifting through a large and chaotic body of material available. So in this age where technology has enabled us to communicate across the globe in practically real time, this is especially the case. And when you're working on covering a developing story, time is especially of the essence and scarce. So what we want an organized and automated way of summarizing this great mass of news articles to quickly identify the most salient points, views, and opinions already expressed by other journalists in this space. What we also would need is the clarity to know where best to direct our time, which is precious as a journalist, in terms of pursuing further leads and deeper research. So fortunately, the same tech that's brought us these new challenges also offers us new tools to be able to tackle these challenges of the digital age. So as a most logical starting point, one might consider using a text summarization algorithm to quickly identify the key points and key players in the story. This works really well for giving us a first overview of the story and the main entities and elements. However, as often the case with summarization algorithms, this could be biased towards the weight of the majority opinion, further amplifying the most prevalent ideas expressed within the story. And by the nature of summaries, we're also leaving out a lot of nuances and outliers in the story. And we're left to trust in the algorithm to present us what it thinks is the most important information that we should be aware of. So in other explorations of different kinds of data, especially in different fields where we work with structured numerical data, one common practice to augment the limitations of simply relying on numerical stats is to visualize the data. In our case, having a text summary is akin to simply viewing the descriptive stats for our data set. So the question is there a way to visualize our unstructured data? The answer is yes. We first have to transform this unstructured textual data into a structured numerical form first. But before moving on, I believe it's important that we take a moment to remind ourselves of just how significant visualizations really are. So in this famous example, often used in data science to impress the limitations of numerical stats alone, we have four identical data sets from the point of view of summary statistics. What it means is it has the same total, the same mean, variance, correlation, even the same regression line. So we might be tempted to think that these identical data sets in terms of its summary stats are from the same population or distribution. However, a visual examination really reveals a different story, as we can see here in this diagram on the right. Although this example may be specifically crafted, it does make the point that the real-world data does conceal a lot of nuances, outliers, and patterns that can be impossible to discern just from numerical stats and observations alone. So this is where visualization offers unique insights and a deeper understanding of our data. So without further ado, here is a visual summary of our cluster of related news articles. All of them are related in the sense that they're from the same developing story. So here we're really able to see the actual shape of the cluster of news articles, the cluster that we've been calling up data set so far. Data points here are represented in a three-dimensional space that properly reflects the semantic relations between all these different articles. So while the units and axes here are meaningless on their own, what matters here is the distance and the relative positions between these different points of different articles. It really reflects the degree of semantic similarity between them. So at a glance, we can observe the contours and the landscape of this news story, where the bulk of coverage converges, such as the core in the middle, where the outliers and the opposing views lie, and perhaps as a way of telling us where to focus our time in pursuing leads and further research as well. So all of this is achieved through a very important technique in NLP called text vectorization, or word embeddings, you might hear as well. So this technique really revolutionized the field of NLP, and it influenced many later models that built upon it. And it was first introduced in 2013 by Tomas Nikolov, a computer scientist at Google. And this model was named Word2Vec. It's the first highly successful model of its kind. It's able to generate word embeddings that really capture the very nuanced meanings in human language. So in a nutshell, what this really means is that this model seeks to translate very abstract concepts of meaning in natural languages to a form that is able to be processed by the computer, which is numerical data, or at its very lowest levels, binary bits. So seen here is usually a very high dimensional vector, which is needed to provide the capacity to capture the great nuance and complexity of human languages. So you can think of each vector here almost as an ID or a key in a dictionary representing a certain meaning. But it also goes beyond that, in the sense that it captures the relation in regards to other words in this predefined high-dimensional space. So in other words, the distance between every vector in this space is really significant, and it matters because the more closely grouped these vectors are, the more closely associated they are in terms of meaning and semantics, and they also tend to be pointing in the same direction. The way in which one would generate these vectors or word embeddings would definitely require a more detailed presentation on its own. But on a high level, one obtains embeddings by training a neural network to recreate these semantic representations by feeding it a large corpus of training data, textual data, usually on the order of millions, if not billions of words. So the goal here for the optimization algorithm is to organize every word into its own vector in a high-dimensional space while preserving the relations between them. And we do this by analyzing a small window of adjacent words in the corpus. So here we see a small window sliding across each sentence in the corpus to really infer from its surrounding words the context and the meaning of the target word. So over time, every observed word in this corpus would be assigned its own vector that hopefully reflects the semantic relations of the training data. So it's important to note here the significance of the training data. As we know, machines by themselves, they're not inherently biased, but they will be shaped by the data we use. So what we can say really is the embeddings that we produce are really a reflection of the training data itself. So now that we've seen how embeddings for individual words are trained, it's not a stretch to extend this concept to entire documents, since documents are, after all, a collection of many individual words. So there are numerous later models in the subsequent years that builds upon the success of word2vec that extends it to larger bodies of text, such as the doc2vec algorithm from Jensen. However, in this example, we are simply taking the average of all the component vectors of a given article or document to represent the embedding for the entire article itself. So as a final additional step before we can visualize our data, we have to convert these very high dimensional vectors to a form that can be visualized. So keep in mind, as we said before, these vectors range from anywhere from 100 to 1,000 dimensions, or in our example, a vector of 300 dimensions. This is far beyond the 3 to 4 dimensions that the human mind can comprehend, even visualize. So to do this, we would employ one of the many techniques in field of transformations known as dimensionality reduction. And here it's also important to acknowledge the trade-off for doing this. So anytime we constrain data to a lower dimension, we risk losing much information in the process, which is by its very nature. The goal, however, is to preserve as much of the properties of data as we can. So one very common technique that we usually employ is principal components analysis, or PCA, which aims to map data to a lower dimension by maximizing the variance in the observed data. So as shown here in this example, when we are going from a two-dimensional to a one-dimensional data representation of the data, we're really going from a plane to a line. So what we want to do here is find the axis or the line that best captures the greatest variance in the data as possible. So this same concept applies to reductions from any dimension, and even higher, much higher dimensions. So in our example, we're using 300 dimensions to 3 dimensions. We follow basically the same concept as a simple 2 to 1D dimension. And that would enable us to visualize the data in a 3-dimensional coordinate space. So as a quick recap of the entire process, we begin with our news aggregator as our source of data, for example, news articles and in a developing story in our case. We would then want to transform these vectors into, the words in these documents into vectors, and then aggregate them by taking the average as a whole to create an embedding for each document. So during this process, it's also important to consider certain text processing steps, for example, lemmatization or stop words, which really, depending on the use case, would give more of an emphasis on capturing the meaning of the article if we were to remove lemmatized the words in the article versus leaving it as it is, where then we're really more focused on capturing the writing style of the entire document as a whole. And the next step then be to reduce these high dimensional vectors using techniques such as PCA to a lower dimensions. So that would be 3 dimensions all lower in order to visualize it. And that brings us to our final step, visualizing our data in a coordinate space. So as described earlier, by taking this vector representation of articles, we are ideally preserving the semantic relations between these different articles in the data set. But here, every data point here basically represents an article within this greater developing story. And the closer they are together, the more similar they are, and vice versa for the ones that are farther apart. And again, this really allows us to quickly discern articles that take on a more mainstream reporting versus ones that diverge and offer conflicting points of views, as seen here in the fringes and the outliers. So in this example, this collection of articles is really taken from the coverage of the current coronavirus pandemic in the US. So it's interesting to see here that the models actually picked up on some political leanings in the coverage of this story. So on the left here, we can see an article from CNBC. It's very much an outlier. On the right here, we can see another outlier on the opposite end of the spectrum from Fox News. And just for good measure, here we have AP News, which is unsurprisingly very close to the core of the cluster. So this doesn't necessarily mean that reporting closer to the core are politically neutral, but it does represent ideas and thoughts that are more mainstream and prevalent in the overall reporting. And indeed, if we were to reduce this to a one-dimensional representation rather than a three-dimensional representation of the data, we would obtain a line that corresponds very much to the political spectrum as we would expect. And again, as we note, this model wasn't trained to discern political leanings, but it just so happens that this happens to be a very prominent feature of the data set. And it's likely the case that publishers at different ends of the spectrum emphasize different aspects of the story or cater to different demographics. So for an entirely different data set, it's entirely our expectation that we would then get different results, where a different feature becomes the most prominent differentiator between these different articles. So to sum up, visual summaries by themselves are no means a replacement for traditional text, but they're a great way to enrich our analysis. For the journalist, these summaries can really offer a quick, comprehensive overview of the entire news landscape at a glance, to quickly be able to discern between different groups of thoughts and reporting. It also acts as an organized starting point for informing further research and helping the journalist to decide where best to spend their limited time and resources. But most importantly, by understanding and visualizing where one falls within the larger landscape of news stories already reported, it really helps us to craft a unique angle for our story to better stand out in a crowded field, or even just to give a voice to a more underreported side of the story. So my name is Daryl Kang. I'm a data scientist at Forbes. Thank you very much for listening.
That was Lai Shawa, data scientist at Lowe's Companies, talking about opportunities of computer vision in retail stores. If you're interested in learning more about how AI can help the retail industry, please subscribe to our channel below.